Welcome back. In our last units, we destroyed the whale with ESI and burned the ocean with ICP. But today, our strategy shifts to the edge. Have you ever wondered why a high-tech coating fails, even when the bulk chemistry is perfect? It's because the secret is hidden on the skin, the very first atomic layer. Today we master SIMS, secondary ion mass spectrometry. We aren't just analyzing a sample, we are performing molecular archaeology. The difference between a bulk analyzer and a SIMS specialist is the dimension of depth. Imagine an onion. Traditional MS tells you the average flavor. SIMS allows us to peel it back, one atomic monolayer at a time, to see exactly what's hidden beneath. We are going to explore how a focused ion beam can map the chemical makeup of a material with sub-nanometer resolution. This is where we find the ghosts in the interface. Our briefing covers 4 strategic sectors. Sector A, the collision cascade. Sector B, static versus dynamic SIMS, reading a cover versus digging a well. Sector C, sub-nanometer forensics, why the Z-axis is your secret weapon. And Sector D, strategic imaging, the ROI of finding impurities that traditional MS simply cannot see. Let's start with the momentum transfer. The difference between an operator and a pro is knowing that we don't just hit the surface, we create a cascade. Think of a break in a game of billiards. The primary ion drives into the lattice, knocking its energy into surrounding atoms. Only the atoms at the very top, the lucky ones, receive enough kickback to be ejected as secondary ions. This is where the truth is gently released. Specialists' insight. Only about 1 in 10,000 particles are ionized. Most of what comes off is neutral. To hack this ionization probability, we use strategic chemistry. As a pro, you don't just choose a beam, you choose a chemical enhancer. Cesium for negatives, oxygen for positives. You are architecting the probability of seeing your analyte. Chapter B, static versus dynamic. Static SIMS uses an incredibly low dose of ions. It's like reading the cover of a book without scratching the ink. You see the intact molecular surface. We use this when we need to map high molecular weight species without destroying the very structures we are trying to identify. It is surgical and pensive. Dynamic SIMS, however, is industrial. We crank up the current and deliberately erode the surface. Imagine digging a well. As we dig deeper, we analyze the water at every foot. This is how we travel through time within a material, uncovering the history written in its layers. This is the industrial standard for semiconductor depth profiling. Chapter C, the Z-axis secret weapon. Why does sub-nanometer resolution matter? In modern electronics, a layer of dopants might only be 5 atoms thick. If your measurement blurs that layer, your data is useless. By using 2F analyzers, we capture everything simultaneously. We are traveling through space as we peel away the material's history. Look at the ROI. SIMS is the gatekeeper for semiconductor quality, measuring parts per billion impurities in thin films. In forensics, it detects chemical signatures even if the oil is gone. If a coating fails, the failure is usually at the interface, the zone SIMS was born to see. You identify what you cannot see in the bulk average. When we combine sputtering with scanning, we get chemical imaging. We move from what is it to where is it exactly, and how deep does it go. We can map exactly where lithium is clustered in a battery electrode. This 3D chemical volume is the gold standard for modern materials, science, and advanced bioimaging. Summary. Depth is the dimension. We've mastered the collision cascade, the duality of static and dynamic SIMS, and the power of 3D mapping. High-sensitivity forensics isn't about the big picture. It's about the localized truth. You are now a molecular archaeologist, equipped to see through the skin of any material. That's all for today. Join me in our next unit, Module 6-4, Fast Atom Bombardment. See you next time.